This classroom lesson is a cooperative effort between the Wisconsin Public Service SolarWise for Schools program and the Create Energy Center. Watts on Our Roof, Lesson 4, Money, Emissions, and Resource Savings. Introduction and Lesson Objectives. Welcome students and teachers to Watts on Our Roof, a series of lessons in which you'll learn from the photovoltaic performance data produced from your solar array. This is Lesson 4, Money, Emissions, and Resource Savings. In this lesson, you'll learn to quantify how a solar array, your solar array, delivers on its promise of saving money, saving pollution emissions from being released into the air, and saving energy resources from having to be extracted and consumed. To quantify these savings, you'll get energy production performance and money-saving data on your system from the eGauge portal. Emissions and resource savings can then be calculated with information you'll locate on two United States Environmental Protection Agency websites, the EPA Power Profiler and the EPA Greenhouse Gas Equivalencies Calculator. Let's begin by establishing and extending money savings from yesterday. On the first of 5 exercises that make up Lesson 4. Unless you parachuted into town last night, you remember yesterday's weather. Follow your teacher's directions to get the current output profile of your solar PV system. You'll probably see something like what you see here. Later in the day production from yesterday and early in the day production from today, both shown in the last 24 hours leading up to this moment. You should know by now what you need to do to place only yesterday's production on a one-day graph. Here we are. Does the weather from yesterday seem to match what you see on your graph? As always, time is the independent variable on the x-axis. Power in kilowatts is the dependent variable on the y-axis. The electrical energy produced for the time period selected, as you know, is always provided here. The first of 5 exercises you'll complete in this lesson is titled Savings from Yesterday. It's the only one of the 5 we'll cover in detail. The 4 exercises that follow are all similar variations on savings from yesterday. Your first step in completing any of these exercises is to copy and paste and then crop a screenshot of the eGauge graph requested in the space provided. Your graph must show both axes, their scales, and the energy generated in kilowatt hours. To accomplish this, delete all the words in the space provided. Then crop and resize your graph to make it fit without expanding the frame. Make sure any personal information on the perimeter of the image is removed by cropping. On your graph, note the energy generated for the time period shown. Post that number in the kWh produced on this day column as you see here. Go back to your graph. Across from energy generated is the money saved during the time period shown. Post that number in the one-day money savings column as you see here. The money savings is based on the residential electricity rate charged in your community, a rate you may be familiar with. It could have been based on several electricity rates used by your energy utility. Using the residential rate gives you the money you would save with this solar PV system in place at your home. This may or may not be a realistic number depending on the size of your school's system. Currently, the average residential PV system installed in America is between 6 and 10 kW. To establish the residential rate, take the one-day money savings and divide it by the kilowatt hours produced on this day. The answer gives you the electricity cost per kilowatt hour, which you'll enter into the table as shown. And to repeat, that rate, the residential rate, is what your utility charges you for the electricity you use in your home. Let's imagine the one-day money savings is an average day. Multiplying it by 365 days in the year will give you 1 year savings. Enter the 1 year money savings in your table. Now we'll establish and extend emission savings from your array yesterday. We'll focus on the 3 primary air emissions saved by using a renewable energy system. They are carbon dioxide, sulfur dioxide, and nitrogen oxides. The first part's easy. You've already determined the energy generated for one day. You may recopy that number in the first column, kWh produced on this day, down the page. Next, you'll go to the United States Environmental Protection Agency Power Profiler webpage to get emissions information. Let's take a brief tour of the Power Profiler splash page. One of the most notable features? The fuel mix chart. It shows the mix of energy resource fuels used in each electricity grid, E-grid, region of the United States. Shown too is the national average mix of resource fuels. Check out the interactive features of this chart. In other places on this page are maps of the individual E-grid regions. Like states, their boundaries are rooted in politics, economics, and historical developments. Elsewhere on the page, you'll find an interactive emissions rates chart organized by E-grid subregions. It charts the 3 atmospheric emissions we're interested in: carbon dioxide, sulfur dioxide, and nitrogen oxides. To zoom in on your E-grid subregion, enter your zip code here and click Go. Just below, it'll give you your E-grid subregion acronym. Mine's the Midwest region, and it'll highlight your region in blue. It'll also compare the fuel mix of just your region to the national average. For example, the natural gas burned in my region is about equal to the national average. But in my region, we burn considerably more coal than the national average. Comparisons like these are interesting and meaningful, but we're here to get the carbon dioxide, sulfur dioxide, and nitrogen oxides emissions rates. Click on CO2 if it's not selected by default. The bar graph will display your region's CO2 emissions in comparison to the national average. In my region, it's close to double the national average. Note the CO2 emissions rate is provided in pounds of carbon dioxide per megawatt hour. You need to convert this to kilowatt hours, a much more standard usable unit. Divide your region's pounds of CO2 emissions per megawatt hour by 1,000 to convert it to kilowatt hours. Enter the quotient into your table. Then multiply to get the pounds of CO2 emissions saved by your solar PV array from going into the air yesterday, and enter it into your data table. Now click on or select SO2. As you can see, even though my region burns a lot more coal than the national average, it releases less SO2 into the atmosphere. Repeat the process you learned just a moment ago with your region's CO2 emissions rate to establish the pounds of SO2 emissions saved by your solar PV array from going into the air yesterday. Now select nitrogen oxides. Establish the pounds of NOx emissions saved yesterday with your solar array by repeating this process. Next, we'll imagine, as we did with money savings, that yesterday was an average day of the year. Each of your emissions savings multiplied by 365 will provide you with the pounds of CO2, SO2, and NOx emissions saved by your array over a full year. That brings us to establishing and extending energy resource savings. You'll go to the Environmental Protection Agency Greenhouse Gas Equivalencies Calculator for the information you need. Here we'll convert the energy data into concrete terms we can better understand. Scroll to Step 1. Enter and convert data. Select Energy Data to convert. Under Enter Data, click on Kilowatt Hours Avoided. Kilowatt hours of electricity saved from being used because your PV system produced them instead. Type the very convenient number of 1 into the amount box. Then enter your zip code to get resource equivalency data specific to your location. Click on Convert Data. A variety of equivalencies to 1 kilowatt hour of electricity avoided in your region will appear. Here are some examples. 1 kWh of electricity avoided in my region is the energy equivalent of 2 miles driven by an average gasoline-powered passenger vehicle. It's also equivalent to about 7/10 of a trash bag of waste recycled instead of landfilled. It's equivalent to almost 1/10 of a gallon of gasoline consumed. In my region, 1 kWh of electricity avoided is the energy equivalent to 54 smartphone chargings. We're after this equivalency, though, the pounds of coal that would have to be burned to generate the 1 kilowatt hour of electricity our solar PV system produced instead. Enter that number into your data table as the pounds of coal equivalent per kWh. Do the multiplication to get the one-day coal equivalent savings. It needs to be said, no region in the United States uses only coal to generate its electricity. So why are we singling out coal? Coal is a legacy fuel in the United States. Interestingly, about 100 years ago, it dominated the energy scene. True, its use has declined in recent decades in favor of cleaner energy resources, but it's still being used in considerable quantity in America. It's also a commodity you're familiar with. You may have held charcoal briquettes in your hands. You have a reference point for it. So take yesterday's one-day coal equivalent savings and multiply it by 365 days. The quantity you get would be the 1-year coal equivalent savings if yesterday was an average day of solar PV production. It's worth taking a moment to appreciate these numbers. Each result you see here. Exercises 2, 3, 4, and 5. Now you'll do all of this a few more times. There are 4 more exercises to complete. The first 3 closely resemble the one you've just completed. The last one is a little different, but similar. In the next, your second exercise, you'll calculate money emissions and resource savings from a great day of solar production, then from a poor day, and then from an average day of solar PV production. But before you begin the next 3 exercises, something needs to change. Here are graphs of 2 different days of solar PV production. At a glance, on which day was more electricity produced? It's impossible to tell much at a glance since both graphs are auto-scaled. However, set to the same scale, it's easy to see which day produced more energy. A lot more, over 11 times more. You're going to set graphs for the next 3 exercises to the same scale for this reason. Set the time period to show in the graph to all of last year. A graph of 365 days of production looking like this appears. On the graph, the greatest day of power production appears to be just under 2 kW. So in this case, we'd set the scale to 5 kW. Set to 1 kW and the graph plot would go above the top of the scale. 10 kW and the plot would be much too small. Once we select 5 kilowatts, all subsequent graphs will stay at 5 kW until changed. Now, to get a great day of solar production, set the time period to show only the first day of June last year. Here it is as an example. Our scale, as expected, is set to 5 kW of power. More important is the energy reading for the day, 5.81 kWh. Click on the single arrow bottom right, advancing to the second day of June. Right away we can see the energy production is higher, 15 kWh. Advance to the next day. June 3rd is obviously lower. Advance again and again through the whole month of June to find the day of highest energy production. Here's my best day of June, a day of cloudless skies that generated 17.4 kWh of electrical energy. For this exercise, then, we'd select June 10 as our great day of solar production. Just like our yesterday exercise, you'll paste in a graph of the day. Enter energy production for the day in the first column of the data table in every row. Then complete the exercise across each row as shown earlier. By the way, you'll be asked later why it makes good sense to look for a great day of solar production in June. Also asked why it makes sense to look for an average day of PV production in March and a poor day in December. Now, we'll get that poor day of solar production. Let's go to December 1st of last year. On December 1st, the array didn't produce even 1 full kilowatt hour of energy. The next day was higher at 2.33 kilowatt hours. Remember, we're looking for the lowest day of production this time. On December 3rd, production is even higher. It turns out that for this December, the 11th was the date for lowest energy production, 354 watt hours. 0.354 kilowatt hours would then be posted as the poor day of solar production. Starting with that number, the rest of exercise 3 may be completed. Our savings from an average day of solar production requires a little different approach. Set the time period to the whole month of March last year. Take the energy generated for the month of March and divide by 31 days to get the daily average for the month. Now go to March 1st. Move through the month of March to select the day that most closely matches the average you calculated. In this case, it's March 8th. Then complete exercise 4 in the same way you learned how to do the others. That brings us to the 5th and last exercise in this lesson, annual and lifetime savings from 1 year of solar production. Begin by setting the time period for all of last year. Here's what the 1-year output profile looks like, set to a scale of 5 kW. There's no reason to keep that scale now, so reset it to auto scale. The graph now occupies most of the available space. Take note of the energy generated number. Like on this graph, it's probably given in units of megawatt hours, MWH. To complete this exercise properly, it must be converted to the unit we've been using all along, the familiar kilowatt hour, kWh. Determine how to do this correctly, then post it into exercise 5 and complete the remainder of the exercise in much the same way as the others. You've now learned how to perform all of the exercises for this lesson. Here's Lesson 4 in review. Your solar array saves money, saves pollution emissions from being released to the air, and saves energy resources from having to be extracted and consumed. Look carefully at the annual and lifetime money, emissions, and resource savings. And make sure to take into account the size of your system when looking at these numbers. The savings numbers here are even more significant than they first appear. These savings come from a small 2.8 kilowatt system, which is roughly 1/3 to 1/4 the size of the average residential size system installed in the United States today. Money, emissions, and resource savings. There's a lot to like about your solar array. Now complete additional work for this lesson assigned by your teacher. Then move on to Lesson 5 of Watts on Our Roof.